So, uh, as I said, the continuous optimization over alpha and theta solves the problem. But as an engineer, you need to know about uncertainty. As a statistician, you should know about uncertainty. You should care about uncertainty. Everything is not prediction, as machine learning and deep learning guys are always talking about. You should enjoy talking to statisticians as well, because they care about uncertainty, they respect uncertainty, and they are very scientific people. So, what is the how can we deal with these things? For example, in order to efficiently sample from the posterior f condition on alpha, theta, these are hyperparameters, and the y, if you want, so this is a high dimensional random variable. So to efficiently sample from that, during history, the simplest scheme invented in history till the most complex scheme man ever created. So there is a spectrum. And for example, here is, for example, Gibbs sampling. So it's very simple, but it doesn't work for everything, and it has its own problems. And then people invented Metropolis Hastings algorithm. If you read that article that Hastings wrote, and after that you get to modern science, which is block Metropolis Hastings, and then more modern approaches, control variables, and there are hundreds, and if not thousands, of articles, especially in arXiv, around this, which is much more advanced than very simple Gibbs sampling. So all of them helps you to do efficient sampling from the posterior. So to give you a flavor, of course, the reason that I like I like Metropolis Hastings algorithm, Langevin MCMC, Hamiltonian MCMC, and those things, is because I love the state space, the Markov chain on the general state space. Because it is not as simple as a finite state, which you just need some eigenvalues and eigenvectors to understand your complex graph. But now it's a mixture of two walls. So you want to use the advanced methods of convergence rates in Markov chains. And there are some techniques such as drift that I will come back to the playlist of Markov chains in the next few months if I had time. Then you will see why I care about these Markov chain Monte Carlo algorithm. Because they are the future of cognitive science, future of machine learning, future of statistics, and the future of computer science in general. Because a Markov chain Monte Carlo is just a simulation. And I don't mean those things that people say about VR in simulation, life is simulation. I don't mean like that. I mean that the brain doesn't use backpropagation. It's not like those deep neural networks. The brain uses simple physical things. For example, look at heat equation. It's just a physical law. It's not, so the computation for a physicist is just a implementation of a physical law and nothing else. There is no mysterious guy inside your brain. It's just a physical law, like quantum mechanics. Everything is just natural. So there is no guy inside your head to do those back propagation, and even back propagation has not been proved to be a physical things inside your mind. And so it's just a simulation. And of course, in those times that Descartes invented that dualism between mind and body, that he said that those are things that are from different things. He didn't know. I mean, Descartes didn't know at that time that Markov chain is such a beautiful thing that you can justify many of the things that happen inside your brain. For example, people are talking about natural language processing, but they are biased by those things, those semantics, instead of doing some cognitive science, like, for example, making some analogy, making some concepts, and taking advantage of Bayesian analysis and Markov chains. Do these two things, Bayesian analysis and Markov chain. Using these two things, you don't need anything else. You don't need deep learning. You don't need back propagation. These are simple things based on simple mathematics like chain rule. So your mathematics of 21st century is reduced to a chain rule, but you ignore the great amount of science that we have about Markov chains and Bayesian analysis, and how they are intuitively related to how mind works. So this is just something that I should write about Markov chain, and I should say that human mind is like a Markov chain, and we should make it more ergodic, to be more creative, to be a better human. And so let's come back to our Metropolis Hastings algorithm. So suppose we want to sample from P of F condition Y. So this is the probability of Y condition F, P of F, and P of Y condition F, P of F, D of F. So the Metropolis Hastings algorithm, it forms a Markov chain. It moves, and after a while you see, oh, it's like a distribution. So this is the power of simulation, because you're not doing some gradient descent. You're just sampling from your moves. For example, random walk, and after some time you notice that it creates a stationary distribution. And so we initialize f of 0, and we consider a proposal distribution q of f of t plus 1 condition on f that allows us to draw a new state given the current state. So the new state accepted with probability minimum of 1 and a, where a is the probability of y condition on f times the probability of f, probability of y condition on f times t, and the probability of ft. And q of f of t plus 1 condition on f of t. Q of f of t condition on ft plus 1. So as you see, because f is high dimensional, finding a good proposal is really challenging. But not that much challenging for those researchers who are active on Markov chains on general state space. And I think that this is enough for today. And next week I will carry on and talk about different aspects of Gaussian processes, and maybe some applications of that to different problems in machine learning. And okay, take care. Cheers.